In most contexts, these effects are extremely small. They average out and have little influence on large-scale behavior. But when gravity is considered, the situation changes. General relativity teaches that energy influences spacetime geometry. Any form of energy, including zero-point energy, contributes to curvature. If quantum fields fluctuate, then the energy associated with those fluctuations should also fluctuate. If energy fluctuates, spacetime geometry should respond. This leads to a striking possibility. At very small scales, spacetime itself may fluctuate. Instead of being a smooth geometric structure, spacetime may exhibit constant rapid variations in curvature. Distances and angles would not be fixed. They would shift and blur due to underlying quantum effects. The classical picture of a stable background would no longer apply. This idea was explored in detail by John Wheeler, a physicist who made major contributions to both general relativity and quantum theory. Wheeler recognized that if quantum mechanics applies to everything else in nature, it should also apply to spacetime itself. He proposed that at extremely small scales, spacetime might be wildly irregular. He described this hypothetical regime as quantum foam. The term is metaphorical, but it conveys an important point. Just as foam consists of bubbles forming, merging, and collapsing, quantum spacetime might involve constant creation and annihilation of geometric features. Tiny distortions, tunnels, or fluctuations could appear and disappear on extremely short timescales. It is important to be clear about what this picture does and does not claim. Quantum foam is not a confirmed description of reality. It is a conceptual image meant to capture the idea that spacetime may not be smooth when examined closely enough. The details depend on the correct theory of quantum gravity, which has not yet been established. Nevertheless, the concept serves an important role. It provides a way to visualize how smooth spacetime might break down without invoking literal discreteness or sharp boundaries. In this view, spacetime is not made of rigid blocks. Instead, it is more like a restless medium whose average behavior appears smooth, while its microscopic behavior is highly irregular. The scale at which this behavior becomes relevant is expected to be near the Planck length and Planck time. At these scales, quantum fluctuations of energy are strong enough to produce significant fluctuations in curvature. The geometry of spacetime would no longer be well defined in the classical sense. This does not mean that spacetime dissolves into chaos in any observable way. These fluctuations would be confined to scales far smaller than anything directly accessible. At larger scales, the fluctuations would average out, producing the smooth geometry described by general relativity. This averaging process is central to why classical spacetime works so well. Just as thermal motion of atoms produces smooth temperature at macroscopic scales, quantum fluctuations of spacetime could produce smooth geometry when viewed from far enough away. The idea of quantum foam also highlights why measurement becomes so difficult at these scales. If spacetime itself is fluctuating, then the concept of a fixed ruler or clock becomes problematic. Any measuring device would be embedded in the same fluctuating geometry it is attempting to measure. This undermines the assumption that distances and durations can be defined independently of the measurement process. Instead, geometry becomes relational and context-dependent. What can be said depends on how the system is probed. Wheeler emphasized that this regime is not one where familiar intuition should be trusted. Concepts such as points, trajectories, and continuous paths may no longer apply. The mathematics used to describe smooth manifolds may fail because the underlying structure does not support them. At the same time, it is crucial to avoid overstating the implications. Quantum foam does not imply that spacetime is literally boiling or unstable in any macroscopic sense. It does not mean that spacetime is tearing itself apart. The effects are confined to scales where classical language breaks down. From a physical standpoint, quantum foam represents a region where known theories overlap but do not fully agree. Quantum mechanics predicts fluctuations. General relativity predicts that energy affects geometry. Combining these predictions suggests fluctuating geometry, but does not provide a complete description. Different approaches to quantum gravity treat this situation differently. Some predict discrete geometric structures, others predict smooth but highly fluctuating geometries. Some suggest that spacetime itself emerges from more fundamental entities that are not geometric at all. What unites these approaches is the rejection of smooth spacetime as a fundamental assumption at all scales. Instead, smoothness becomes something that emerges when fluctuations are averaged over large distances and long times. The imagery of quantum foam helps bridge the gap between abstract theory and physical intuition. It allows one to think about spacetime not as a static stage, but as an active participant subject to quantum effects. This shift in perspective is significant. Once spacetime is allowed to fluctuate, it becomes clear why attempts to quantize gravity face such difficulties. The object being quantized is not a field within spacetime, but spacetime itself. It also clarifies why classical geometry reappears so reliably. The foam does not disappear. It becomes irrelevant at scales where fluctuations cancel out and geometry stabilizes. In that sense, quantum foam is not a competing description of spacetime. It is a candidate for what lies beneath it. Whether this picture is correct remains an open question. What matters here is the role it plays in thinking about quantum spacetime. It provides a concrete way to imagine how continuity might fail without abandoning physical realism. Spacetime in this view is neither perfectly smooth nor fundamentally broken. It is structured in a way that depends on scale. At large scales, it behaves like a continuous geometric entity. At the smallest scales, it may be dominated by quantum fluctuations that defy classical description. This non-smooth microscopic picture marks a transition in the discussion. The focus shifts from whether spacetime can be treated as smooth to what replaces smoothness when it cannot. The language necessarily becomes more tentative here, not because physics becomes speculative, but because current theories reach their limits. What can be said with confidence is limited but not trivial. Quantum fluctuations of spacetime offer a coherent reason why smooth geometry should fail at small scales while remaining accurate at large ones. They connect quantum uncertainty, gravitational response, and the emergence of classical spacetime into a single conceptual framework. This does not provide a final answer. It provides a direction. It suggests that spacetime's quantum nature, if it exists, is not static or discrete in a simple sense, but dynamic, relational, and scale-dependent. The imagery of foam may not survive future theories. The underlying insight likely will. The phrase quantum foam is often the first image people encounter when thinking about spacetime at the smallest scales. It suggests motion, instability, and structure, where classical physics expects smoothness. As an idea, it is useful. As a literal description, it can be misleading. Understanding what the term is meant to convey and what it is not is essential. At its core, quantum foam is an attempt to describe what spacetime might be like when quantum effects become unavoidable. It arises from combining two well-established facts. Quantum mechanics predicts unavoidable fluctuations in energy. General relativity predicts that energy affects spacetime geometry. If both statements are taken seriously, then spacetime geometry itself should fluctuate at sufficiently small scales. That conclusion is conceptually straightforward. Visualizing it is not. The human mind tends to picture space as an empty container and time as a flowing sequence. Foam suggests bubbles forming and popping within that container. This is not what is meant. There is no background space in which spacetime foam sits. The fluctuations are not happening in spacetime. They are fluctuations of spacetime. This distinction matters. When John Wheeler introduced the term, he was not proposing a specific physical structure. He was pointing to a regime where classical geometric language breaks down. The foam was meant to signal the loss of smoothness and predictability, not to specify the exact form of what replaces it. At extremely small scales, the quantities that define geometry in general relativity, such as distance, angle, and curvature, may not have stable values. Instead of a single well-defined geometry, there may be a range of possible geometries, each contributing probabilistically. In that sense, spacetime would behave more like a quantum system than a classical object. The word foam captures this multiplicity. It suggests a constantly changing pattern rather than a fixed structure. But it is a metaphor, not a model. Metaphors are useful because they allow unfamiliar ideas to be discussed using familiar language. They are dangerous when taken too literally. Quantum foam does not imply bubbles of space, popping in and out of existence in any simple or observable way. It does not imply turbulence or motion that could be detected by instruments. It does not imply instability at scales larger than the Planck regime. The foam, if it exists, would be confined to scales far smaller than anything that could influence ordinary physics. One way to keep this grounded is to remember that the foam is not a claim about appearance. It is a claim about calculation. When physicists attempt to describe spacetime using quantum principles, the mathematics suggests that contributions from many possible geometries must be considered. The smooth geometry of general relativity appears only as an average over these possibilities. In this sense, the foam is statistical rather than mechanical. It is not a substance. It is a way of talking about uncertainty and fluctuation in geometry. This also explains why visualization is limited. Human intuition is built around objects moving through space over time. Quantum foam challenges both ideas at once. There may be no fixed objects, no stable background, and no single timeline. Any picture that resembles familiar physical scenes is likely to mislead. This is why careful language is important. Saying that spacetime is foamy does not mean it is chaotic in the everyday sense. It means that classical descriptions fail to capture its behavior at certain scales. It also means that different theories can use the same metaphor while meaning different things. In some approaches to quantum gravity, spacetime is fundamentally discrete. In others, it is continuous but subject to large quantum fluctuations. In still others, spacetime emerges from more basic entities that are not geometric at all. All of these approaches might be loosely described as involving quantum foam, but they are not equivalent. The metaphor unifies them only at a very high level. This is where speculation enters the picture. Quantum foam has not been observed. There's no experimental evidence that directly confirms or rules out its existence. Its status is theoretical, inferred from the attempt to reconcile quantum mechanics with gravity. That makes it a plausible idea, not an established fact. Acknowledging this is not a weakness, it is a strength. Physics progresses by clearly distinguishing what is known, what is inferred, and what is unknown. What is known is that quantum fields fluctuate. What is known is that energy affects spacetime geometry. What follows from combining these facts depends on assumptions about how quantum principles apply to spacetime itself. That is where different theories diverge. The foam metaphor helps prevent a different kind of misunderstanding as well. It discourages the idea that spacetime must either be perfectly smooth or completely broken into rigid pieces. The reality may be more subtle. Spacetime may lack a fixed structure at small scales without being composed of simple building blocks. This middle ground is difficult to describe without imagery, which is why metaphors persist despite their limitations. Another important point is that quantum foam does not imply randomness without structure. Quantum mechanics is probabilistic, but it is not arbitrary. Probabilities follow precise mathematical rules. If spacetime fluctuates quantum mechanically, those fluctuations would also follow well-defined laws, even if the outcomes are not deterministic. From this perspective, foam does not mean disorder. It means indeterminacy constrained by physical principles. The usefulness of the concept lies in how it reframes expectations. Instead of assuming that spacetime must remain smooth at all scales, It allows for the possibility that smoothness is an emergent property. Instead of expecting a single geometry, it allows for many possible geometries contributing collectively. This prepares the ground for more formal approaches. Once the metaphor has done its job, it must be set aside. Progress depends on precise mathematical frameworks, not imagery. The foam is a bridge, not a destination. It also serves as a caution. Overly concrete images can create false confidence. Thinking of spacetime as frothy or bubbling can make the unknown feel familiar when it is not. The goal here is not comfort, but clarity. In summary, quantum foam is best understood as a conceptual signal. It marks the breakdown of smooth spacetime at very small scales. It captures the idea that geometry itself may be subject to quantum uncertainty. It does not specify the detailed structure of spacetime, nor does it claim direct observability. Treating it as a metaphor keeps it useful. Treating it as a literal picture leads to confusion. With that distinction in place, attention can shift toward theories that attempt to describe quantum spacetime without relying on imagery. The foam has served its purpose by loosening classical assumptions. What comes next requires more precise tools. One serious attempt to reconcile quantum mechanics with gravity begins by taking general relativity at face value. Instead of treating gravity as a force added to quantum theory, this approach starts with spacetime itself and asks how its geometry might behave if quantum principles are applied directly to it. This line of thought is known as loop quantum gravity. The central idea behind loop quantum gravity is straightforward in spirit, even if technically demanding. If spacetime is dynamic, as general relativity insists, and if quantum mechanics applies universally, then spacetime geometry itself should be subject to quantization. Distances, areas, and volumes should not vary continuously without limit, but should come in discrete amounts. This approach does not attempt to unify all forces of nature. It does not introduce extra dimensions or new particles beyond those already known. Its goal is narrower but deeper. It aims to describe the quantum properties of spacetime itself. Two physicists closely associated with the development of this framework are Carlo Rovelli and Lee Smolin. Working independently and collaboratively from the late 20th century onward, they helped shape the mathematical structure of loop quantum gravity and clarify its physical interpretation. One of the key conceptual moves in loop quantum gravity is the abandonment of a fixed background spacetime. This choice aligns the theory closely with general relativity. There is no predefined geometry on which quantum processes unfold. Instead, geometry is part of the quantum system. This makes loop quantum gravity a background-independent theory. Spacetime does not exist first, with quantum effects layered on top. Geometry emerges from the quantum states themselves. To describe these states, the theory introduces a new way of representing geometry. Instead of smooth fields defined at every point, geometry is encoded in networks of discrete elements known as spin networks. A spin network is not a physical object embedded in space. It is a mathematical structure that represents how areas and volumes are related. The nodes of the network correspond to elementary chunks of volume. The links between nodes correspond to elementary areas. Together they define a quantum state of geometry. Each link carries a quantum number that determines the amount of area it represents. Each node carries information about volume. These quantities are not continuous. They take on discrete values, much like the energy levels of an atom. This leads to one of the most striking predictions of loop quantum gravity. Geometric quantities such as area and volume have minimum non-zero values. There is a smallest possible area and a smallest possible volume. Space in this sense is not infinitely divisible. It is important to state this carefully. Discreteness here does not mean that space is made of tiny cubes arranged on a grid. The geometry is relational rather than lattice-like. The spin network does not sit inside space. It defines space. At large scales, when many such elements are involved, the discrete structure becomes indistinguishable from a smooth continuum. The familiar geometry of general relativity emerges as an approximation, just as fluid flow emerges from molecular motion. This emergence is central to the credibility of the theory. Any viable approach to quantum gravity must reproduce classical spacetime at scales where general relativity has been tested. Loop quantum gravity is constructed so that this limit exists in principle, though demonstrating it in full detail remains an active area of research. Time is treated differently as well. In loop quantum gravity, there is no single universal time parameter. Instead, change is described relationally. Physical quantities evolve with respect to one another rather than with respect to an external clock. This reflects a lesson already present in general relativity. Time is not an absolute background variable. It is tied to the geometry and matter content of the universe. Loop quantum gravity extends this idea into the quantum domain. One consequence of this is that the theory does not predict spacetime foam in the pictorial sense often imagined. Instead of wildly fluctuating geometry at every scale, the theory predicts a granular but well-defined structure. The uncertainty lies in which spin network configuration describes a given situation, not in the stability of the geometry once a configuration is specified. This distinction matters. Loop quantum gravity does not suggest that spacetime becomes chaotic at small scales. It suggests that spacetime has a definite quantum structure, governed by precise mathematical rules. These rules lead to specific predictions. One of the most studied concerns the fate of classical singularities. In certain simplified models, loop quantum gravity replaces singularities with finite, well-behaved quantum states. Instead of infinite density, the theory predicts a transition through a minimum volume. Applied to cosmology, this idea leads to scenarios in which the classical beginning of expansion is replaced by a quantum bounce. The universe contracts to a very small but finite size, then expands again. Time does not end. The classical description simply ceases to apply. It is important to be clear about the status of these results. They are derived within simplified settings that capture key features of the full theory, but do not represent complete solutions. They demonstrate consistency rather than certainty. Another area of interest is black hole physics. Loop quantum gravity predicts that the area of a black hole horizon is quantized. This provides a microscopic explanation for black hole entropy, connecting geometric degrees of freedom to thermodynamic behavior. Here again, the results are suggestive rather than final. They show that the theory can reproduce known semi-classical results, while offering new insight into their origin. Despite these successes, loop quantum gravity faces significant challenges. The mathematics is complex. Connecting the discrete quantum geometry to smooth spacetime in all situations is technically demanding. Making contact with experiment is difficult because the predicted effects occur at scales far beyond current reach. There is also the question of completeness. Loop quantum gravity focuses on spacetime geometry and gravity. It does not automatically incorporate the other fundamental forces or the particles described by the standard model. Whether and how these elements can be included remains an open problem. These limitations are acknowledged by researchers working in the field. They are not viewed as failures, but as indicators of how difficult the problem truly is. What gives loop quantum gravity its standing as a serious candidate theory is not that it provides all the answers, but that it is built on clear principles. It respects the background independence of general relativity. It applies quantization to geometry itself. It produces concrete, testable mathematical predictions, even if those predictions are currently inaccessible. Equally important is what the theory does not assume. It does not rely on extra dimensions. It does not require unobserved symmetries. It does not posit a pre-existing spacetime arena. Everything begins with the geometry we already know and asks how it behaves under quantum rules. This makes loop quantum gravity conceptually conservative, even as it is mathematically radical. Its picture of spacetime is neither perfectly smooth nor wildly fluctuating. It is discrete, relational, and structured. Smoothness emerges only when many quantum geometric elements are considered together. This offers one clear answer to the question of when spacetime becomes quantum. In this approach, spacetime is always quantum. What changes with scale is whether that quantum nature is visible or hidden by averaging. At large scales, quantum geometry looks classical. At small scales, discreteness becomes unavoidable. Loop quantum gravity does not claim to be the final word, it claims to be a consistent step. It shows that it is possible to construct a theory in which spacetime itself is quantized without abandoning the core insights of general relativity. Whether this approach is correct remains unknown. What it provides is a concrete example of how the smooth spacetime of experience might arise from a deeper quantum structure, and how continuity could fail without destroying coherence. In doing so, it sets a standard against which other approaches can be compared. Another major attempt to understand quantum spacetime begins from a very different starting point. Rather than quantizing spacetime geometry directly, this approach asks whether the basic ingredients of matter and force have been correctly identified in the first place. This line of thought leads to what is known as string theory. The core premise of string theory is simple to state. The fundamental constituents of nature are not point-like particles, but extremely small extended objects called strings. These strings can vibrate in different ways. Each pattern of vibration corresponds to a different particle, with its own mass and properties. In this picture, particles such as electrons, quarks, and even force carriers are not fundamentally distinct. They are different modes of the same underlying object. What appears as diversity at low energies is unity at the smallest scales. This idea emerged in the late 20th century as physicists searched for a consistent way to describe gravity using quantum principles. Early attempts to quantize gravity directly ran into the problem of uncontrollable infinities. String theory offered a way around this by softening interactions at very small distances. Point particles interact at single locations, leading to sharp divergences in calculations. Strings, by contrast, have spatial extent. Interactions are spread out along the string, which smooths out the behavior at short distances. This mathematical feature turns out to be crucial. One of the most important results of string theory is that gravity is not added by hand. It appears naturally. Certain vibrational modes of strings behave exactly like a quantum particle that carries gravitational interaction. In other words, a quantum description of gravity emerges automatically from the theory. This was a major motivation for pursuing the framework further. A single theoretical structure seemed capable of incorporating both quantum mechanics and gravity, something no other approach had achieved so cleanly. The ambition of string theory goes beyond gravity alone. Its broader goal is unification. It aims to describe all fundamental forces and particles within a single, consistent framework. Electromagnetism, the nuclear forces, and gravity would all arise from the same underlying dynamics. This unifying ambition has shaped much of theoretical physics over the past several decades. Large communities of researchers have explored the mathematical structure of string theory, often working in close dialogue with developments in particle physics, cosmology, and mathematics. The research culture surrounding high-energy physics reflects this. Ideas developed in string theory circulate through conferences, institutes, and collaborations associated with major experimental centers, including those focused on particle collisions and fundamental interactions. Even when string theory itself cannot be tested directly, its influence shapes how questions are framed, and which problems are considered meaningful. One of the most striking features of string theory is that it requires more dimensions of space than are directly observed. In its simplest consistent forms, string theory requires a total of 10 spacetime dimensions. That means 9 dimensions of space, and 1 of time. Other versions require even more. This immediately raises an obvious question. If extra dimensions exist, why are they not seen? The standard answer is that these additional dimensions are compactified. They are curled up into extremely small shapes, far smaller than any scale that could be detected with current technology. At human and even atomic scales, these dimensions would be invisible. An analogy is often used here with caution. A long cable looks one-dimensional from a distance. Only when examined closely does its circular cross-section become apparent. Similarly, space might have additional dimensions that only become apparent at extremely small scales. It is important not to take this analogy too literally. The mathematics of compactified dimensions is highly sophisticated and involves complex geometric structures. What matters conceptually is that spacetime in string theory is richer than the three-dimensional space of experience. These extra dimensions are not optional. They are required for mathematical consistency. Without them, the theory develops internal contradictions. This is both a strength and a weakness. It provides a clear structure, but it also places string theory far beyond direct experimental test. Spacetime, in this framework, is not fundamentally quantized in the same way as in loop quantum gravity. Instead, the smoothness of spacetime emerges because the fundamental objects interacting within it are extended. The strings smear interactions over small distances, preventing the formation of singularities in the same way point particles would. In this sense, string theory addresses the problem of quantum spacetime indirectly. It does not begin by discretizing geometry. It modifies the behavior of matter and forces so that spacetime remains well-behaved even at very small scales. This leads to a different intuition. Rather than spacetime breaking into discrete chunks, spacetime remains continuous, but the physics occurring within it is softened at short distances. Singularities are avoided not by quantizing geometry itself, but by changing what interacts within that geometry. This distinction matters when comparing approaches. Loop quantum gravity predicts discrete geometric quantities. String theory predicts smooth geometry with new degrees of freedom that prevent breakdowns. Both approaches aim to resolve the same problem, but they do so using different assumptions. String theory also introduces a powerful idea known as duality. Different physical descriptions which appear unrelated can turn out to be mathematically equivalent. A theory defined in one spacetime geometry may describe the same physics as a theory defined in a very different geometry. One important example of this idea connects gravity in a higher dimensional spacetime to a quantum field theory defined on its boundary. This suggests that spacetime geometry might emerge from more fundamental non-geometric degrees of freedom. Distance and volume could be derived quantities rather than primitives. This has led some physicists to suggest that spacetime itself is not fundamental in string theory. Instead, it arises from patterns of interaction within a deeper framework. In that view, asking when spacetime becomes quantum may be the wrong question. Spacetime may be an effective concept that only appears under certain conditions. Despite its mathematical richness, string theory faces serious challenges. The most significant is testability. The characteristic scales at which string effects become important are expected to be close to the Planck scale. This places them far beyond the reach of current or foreseeable experiments. No direct experimental evidence supports the existence of strings or extra dimensions. There's also the issue of uniqueness. String theory does not produce a single, clearly defined universe. Instead, it allows an enormous number of possible solutions, each corresponding to different physical constants and properties. Explaining why the universe has the particular structure observed becomes difficult. Supporters argue that this flexibility may be a feature rather than a flaw. It may reflect the true complexity of fundamental physics. Critics argue that without predictive power, the theory risks becoming disconnected from observation. These debates are ongoing and active. They are part of what makes string theory both influential and controversial. What matters for the question of quantum spacetime is not whether string theory is correct, but what it demonstrates. It shows that there are multiple coherent ways to approach the problem. One can attempt to quantize geometry directly, or one can modify the underlying constituents of matter so that geometry remains smooth. String theory occupies the second path. It offers a vision in which spacetime does not fragment or fluctuate wildly at small scales. Instead, the violent infinities that plague point particle theories are avoided because interactions are fundamentally extended. Geometry remains continuous, but its meaning is tied to deeper structures. This broadens the theoretical landscape significantly. It shows that quantum spacetime does not have a single obvious form. Different assumptions lead to different pictures, each internally consistent and grounded in established physics. In that sense, string theory complements rather than replaces other approaches. It provides a contrasting answer to the same underlying question. How can quantum mechanics and gravity coexist without contradiction? Whether spacetime becomes quantum through discreteness, emergence, or extended interactions remains unresolved. String theory shows that smooth spacetime might survive at all scales, not because it is fundamental, but because the objects within it are. This perspective does not settle the issue, it deepens it. By offering a radically different route to quantum spacetime, string theory forces the question to be asked more carefully. What exactly is meant by spacetime becoming quantum? Is it geometry that changes, or the entities that give geometry meaning? These questions remain open. What is clear is that string theory has reshaped how physicists think about spacetime, scale, and unification. Even if it turns out not to describe nature directly, its influence on the search for quantum spacetime is undeniable. It stands as a reminder that the path from smooth spacetime to quantum reality may not be singular, and that the correct description may lie deeper than geometry itself. One of the most far-reaching ideas to emerge from attempts to understand quantum spacetime is that spacetime itself may not be fundamental. Instead of being a basic ingredient of reality, it may arise from deeper processes, much as other familiar physical quantities do. This proposal shifts the problem in a subtle but important way. Rather than asking how to quantize spacetime, it asks whether spacetime needs to be quantized at all. It asks whether smooth geometry is something that exists at the most basic level, or whether it appears only when many underlying degrees of freedom are considered together. Physics already contains several examples of this kind of emergence. Temperature feels like a basic property of matter. Objects are hot or cold. Temperature can be measured precisely and behaves predictably. Yet temperature does not exist at the level of individual particles. A single atom does not have a temperature. Temperature emerges only when many particles interact and exchange energy. It is a collective property, not a fundamental one. The same is true of pressure. Pressure describes how strongly a gas pushes on the walls of a container. It can be calculated, measured, and used reliably in engineering. But pressure is not a property of a single molecule. It arises from countless collisions averaged over time. Fluids provide another useful comparison. Water appears smooth and continuous when flowing through a river. The equations of fluid dynamics describe this motion accurately at large scales. At smaller scales, water is composed of discrete molecules moving chaotically. The smooth flow is real, but it is not fundamental. It emerges from underlying microscopic behavior. These examples show that a description can be accurate and indispensable without being fundamental. Emergence does not mean illusion. It means scale dependence. Applied to spacetime, this suggests that distance, duration, and geometry may play the same role as temperature or pressure. They may describe collective behavior rather than microscopic structure. At large scales, spacetime behaves smoothly and predictably. At small scales, the concept of spacetime may dissolve into something more basic. This perspective reframes earlier difficulties. The incompatibility between quantum mechanics and general relativity may arise not because spacetime needs to be quantized in the usual sense, but because spacetime itself is not the right object to quantize. If spacetime is emergent, then quantum mechanics and gravity may be operating at different descriptive levels. Quantum mechanics would govern the fundamental degrees of freedom. Spacetime geometry would describe their large-scale organization. This idea appears in several modern approaches to theoretical physics, most notably in work related to holography. The holographic principle proposes that the information contained within a region of space can be described entirely by data on its boundary. The name comes from an analogy with holograms, where a two-dimensional surface encodes a three-dimensional image. In physics, the idea suggests that volume and geometry may not be primary. They may arise from more fundamental lower-dimensional descriptions. A concrete realization of this idea was proposed by Juan Maldacena in the late 1990s. He discovered a precise mathematical relationship between two very different kinds of theories. One describes gravity in a higher dimensional spacetime. The other describes a quantum field theory without gravity in a lower dimensional setting. Remarkably, these two descriptions encode the same physics. Calculations performed in one can be translated into calculations in the other. Spacetime geometry on one side corresponds to quantum interactions on the other. The significance of this result lies not in the technical details, but in what it implies conceptually. It suggests that spacetime geometry can emerge from quantum degrees of freedom that do not themselves live in spacetime in the usual sense. Distance, curvature, and gravity become derived concepts rather than starting points. In this framework, spacetime is not quantized directly. Instead, quantum mechanics governs a more fundamental system, and spacetime appears when that system is described at large scales or low energies. This changes how the question of quantum spacetime is posed. If spacetime is emergent, then asking when spacetime becomes quantum may be misleading. Spacetime may never be quantum in the same way particles are. Instead, the underlying system is quantum and spacetime inherits properties from it. This would explain several puzzling features encountered earlier. The appearance of a minimum length and time scale may reflect limits on how spacetime emerges, not discrete building blocks of space and time. Singularities may signal the breakdown of the emergent description rather than physical infinities. Quantum foam may reflect uncertainty in the underlying degrees of freedom rather than literal fluctuations of geometry. Emergence also helps explain why spacetime behaves so classically, across such a wide range of scales. Just as temperature behaves smoothly, even though it arises from quantum particles, spacetime geometry could behave smoothly, even if it arises from fundamentally quantum processes. This does not mean that spacetime is less real. Emergent phenomena are real. Pressure can rupture containers. Temperature drives engines. Fluid flow shapes landscapes. Emergence describes how reality is organized, not whether it exists. However, emergent descriptions have limits. They work only when the conditions that support them are met. When those conditions fail, the description must be replaced. In the case of spacetime, those conditions may involve scale, energy, and organization of underlying degrees of freedom. At everyday and astronomical scales, spacetime emerges robustly. At extreme densities or small scales, it may fail. This view also clarifies why no experiment has yet detected spacetime discreteness or quantum fluctuations directly. If spacetime is emergent, then probing its underlying structure would require accessing the fundamental degrees of freedom from which it arises. These may be far removed from geometric concepts and inaccessible to current technology. Importantly, emergence does not eliminate the need for precise theory. It demands it. One must specify what spacetime emerges from, how it emerges, and under what conditions the emergent description applies. These questions are technically demanding and remain open. Different approaches propose different answers. Some suggest spacetime emerges from quantum entanglement patterns. Others propose more abstract mathematical structures. Some retain geometry at a fundamental level, others do not. What unites these approaches is a shift in emphasis. Spacetime is no longer assumed to be the stage on which physics happens. It becomes part of the outcome. This shift has philosophical implications as well. If spacetime is emergent, then familiar notions such as locality and simultaneity may also be emergent. The idea that events occur at definite places and times may apply only within the emergent regime. At deeper levels, relationships may not map cleanly onto spatial separation or temporal order. This does not undermine causality or physical law. It reframes them. Causes and effects may still be linked, but not always in ways that correspond to classical spacetime intuition. The emergence perspective also encourages caution. It warns against assuming that concepts successful at one scale must apply universally. It suggests that the breakdown of smooth spacetime at small scales is not a failure of physics, but a sign that the wrong variables are being used. Seen this way, the central question evolves. Instead of asking when spacetime becomes quantum, the focus shifts to when spacetime stops being the right language altogether. This reframing does not provide final answers. It changes the terrain on which answers are sought. It opens the possibility that spacetime, like temperature or pressure, is a powerful but limited concept. That possibility reshapes how the problem of quantum gravity is approached. It suggests that reconciliation may not come from forcing two incompatible frameworks together, but from recognizing that they describe different layers of reality. At large scales, spacetime geometry describes the organization of matter and energy. At small scales, quantum rules govern the underlying constituents. The challenge is not to choose one description over the other, but to understand how they connect. Emergent spacetime offers one coherent way to think about that connection. It preserves the success of general relativity without insisting on its universality. It respects quantum mechanics without demanding that spacetime behave like a particle. Whether this picture is correct remains unknown. What it provides is a powerful conceptual lens. It allows the question of quantum spacetime to be asked with greater precision and fewer assumptions. Spacetime may not become quantum in the way matter does. It may become irrelevant, replaced by deeper structures that only resemble space and time when viewed from far enough away. That possibility does not diminish the reality of spacetime. It places it in context. Understanding that context prepares the ground for broader reflection. If spacetime is emergent, then questions about meaning, causality, and reality itself must be reconsidered carefully, without abandoning the rigor that physics demands. Ideas about quantum spacetime are ambitious, mathematically rich, and often far removed from direct observation. This raises an unavoidable question. If spacetime becomes quantum only at extreme scales, what can experiments actually test, and where do the limits of observation lie? The difficulty begins with scale. Quantum spacetime effects are expected to become significant near the Planck length and Planck time. These scales are enormously smaller than anything that can be probed directly. Even the most energetic particle accelerators fall many orders of magnitude short of the energies required to resolve such distances. This is not a temporary limitation. It reflects fundamental constraints set by gravity and quantum mechanics themselves. As a result, no experiment can directly look at spacetime at the scale where quantum effects are expected to dominate. There is no microscope powerful enough to see it, and no detector that can isolate such short intervals without disturbing the system beyond recognition. This does not mean that experiment has nothing to say. It means that tests must be indirect. Physics often advances this way. Atoms were accepted long before individual atoms could be imaged. Neutrinos were proposed decades before they were detected. In each case, theory made predictions about observable consequences at accessible scales. The same approach applies here. One promising observational arena involves gravity under extreme conditions. Gravitational waves provide a particularly important example. These waves are distortions in spacetime itself, produced by accelerating masses such as merging black holes and neutron stars. The detection of gravitational waves by the LIGO collaboration confirmed a key prediction of general relativity. The observed signals matched theoretical models with remarkable precision. This success reinforces confidence in the classical description of spacetime at macroscopic scales. At the same time, gravitational wave observations push gravity into regimes that were previously inaccessible. Black hole mergers involve enormous energies and strong spacetime curvature. By comparing observed signals to theoretical predictions, physicists can test whether general relativity continues to hold under these conditions. So far, it does. No deviations from classical predictions have been observed. This places important constraints on proposed theories of quantum gravity. Any viable theory must reproduce the observed behavior of gravitational waves to high accuracy. Exotic effects that would noticeably alter these signals are ruled out. This illustrates a key point. Even without direct access to Planck-scale physics, experiments can still eliminate large classes of speculative ideas. The absence of observed anomalies is itself a form of evidence. Another potential testing ground lies in cosmology. The large-scale structure of the universe carries imprints of its early history. Tiny variations in the distribution of matter and radiation reflect conditions in the very early universe. Some theories of quantum spacetime predict subtle modifications to these patterns. Measurements of the cosmic microwave background radiation, for example, provide a snapshot of the universe when it was only hundreds of thousands of years old. These measurements are extraordinarily precise. They constrain how space expanded, how matter clustered, and how energy was distributed. Any theory proposing radical departures from classical spacetime must be consistent with these observations. So far, the data strongly support the standard cosmological model, based on general relativity and quantum field theory, applied to matter, not spacetime itself. This again narrows the field. Quantum spacetime effects, if they exist, must be subtle enough to leave the early universe largely unchanged at observable scales. Laboratory experiments also play a role, though a limited one. Precision measurements of quantum systems can test whether spacetime behaves classically down to very small scales. Experiments involving atomic clocks, interferometers, and quantum coherence probe how well quantum mechanics and relativity coexist in everyday conditions. These experiments have confirmed both theories with increasing accuracy. Time dilation has been measured over height differences of less than a meter. Quantum superpositions have been maintained over macroscopic distances. No breakdown of classical spacetime has been observed in these regimes. This places strong lower bounds on where quantum spacetime effects could appear. If spacetime has a granular or fluctuating structure, it must be hidden well below the scales currently accessible. It is also important to recognize what experiments cannot test. Many proposed effects of quantum spacetime are intrinsically unobservable with present or foreseeable technology. For example, tiny fluctuations in geometry at the Planck scale would average out over any realistic measurement. Their direct detection would require sensitivity far beyond physical limits, imposed by noise, energy, and gravity itself. This is not a failure of ingenuity. It is a consequence of how nature behaves. There is also a conceptual limit. Some questions may not correspond to observable distinctions. If two descriptions of quantum spacetime produce identical predictions at all accessible scales, no experiment can distinguish between them. In that case, the difference may be one of interpretation rather than physics. This situation is not unique. In quantum mechanics, different mathematical formulations can describe the same, observable phenomena. Physics progresses by focusing on what can be tested, not by insisting that every theoretical detail must be experimentally resolved. Recognizing these limits is part of scientific maturity. The role of experiment in this context is therefore selective. It does not provide direct images of quantum spacetime. It constrains theories by demanding consistency with everything that is already known. It rules out ideas that conflict with observation, and it leaves open those that do not. This balance is delicate. On one hand, theory must remain connected to experiment. On the other, The absence of direct tests does not automatically disqualify theoretical work, especially when it addresses deep inconsistencies in existing frameworks. The history of physics contains many examples where theory ran ahead of experiment for long periods. The key requirement is that theories remain grounded in established principles and produce clear, testable consequences in principle, even if not immediately. This is where caution is essential. Claims that quantum spacetime effects are just around the corner should be treated skeptically. At the same time, dismissing all such work as unscientific ignores how foundational progress is made. Experiments set the boundaries, theory explores the interior, gravitational wave astronomy, precision quantum measurement, and cosmological observation together define a broad experimental framework. Within that framework, spacetime behaves classically to a very high degree of accuracy. Any quantum description must reproduce this behavior. Beyond that framework lies uncertainty, not because science has failed, but because the questions being asked push against the limits of what can be measured. Understanding what experiments can and cannot test helps clarify the status of quantum spacetime. It is not an idea floating free of reality. It is constrained, shaped, and guided by observation, even when it ventures far beyond current reach. This grounding matters. It prevents speculation from drifting into fantasy. It ensures that discussions of quantum spacetime remain anchored to physical reality, even when that reality cannot yet be fully explored. With thus constraints in mind, the remaining task is to assess what is known, what is unknown, and what may remain unknowable. That distinction defines the true frontier. At this point, the shape of the boundary becomes clearer. Physics has carried its most successful theories as far as they can reliably go, and beyond that edge, the landscape changes. Not into speculation without discipline, but into questions that current tools cannot yet answer. General relativity provides a precise and tested description of spacetime as a smooth geometric structure. It explains gravity, cosmic expansion, black holes, and gravitational waves with extraordinary accuracy. Within the regimes where it has been tested, it shows no sign of failure. Its equations remain well behaved, its predictions consistent with observation. Quantum mechanics is equally successful. It describes matter, energy, and fields at small scales with unmatched precision. Its probabilistic framework underpins modern technology and experimental physics. No alternative theory has ever surpassed its predictive power in its domain. Each theory, taken on its own terms, works. The boundary appears when both are applied at once. When gravity is weak and scales are large, quantum effects fade into the background. When quantum effects dominate and gravity is negligible, spacetime can be treated as fixed. The difficulty arises in the narrow overlap where gravity is strong and quantum behavior cannot be ignored. That overlap defines the frontier. At present, physics does not possess a complete, experimentally confirmed theory that describes spacetime under those conditions. Attempts exist. Some treat geometry as quantized. Some treat spacetime as emergent. Some modify the nature of fundamental objects. All are mathematically sophisticated. None have been verified. This is where current theories stop being sufficient. They do not stop working abruptly. They stop answering certain questions. General relativity predicts singularities, but does not describe what happens at them. Quantum mechanics predicts fluctuations, but does not specify how spacetime responds. Together, they point to a regime where familiar concepts lose meaning without being replaced by agreed alternatives. That regime is not vague. It is sharply constrained by known physics. The Planck scale marks where quantum uncertainty, gravitational interaction, and spacetime structure converge. Below that scale, standard notions of distance and duration cease to have operational meaning. Above it, classical spacetime works extremely well. This is not ignorance in the ordinary sense, it is a structural boundary. Within physics, it is important to distinguish between what is unknown and what may be unknowable. Unknown questions are those that current theories cannot answer, but future theories might. For example, whether spacetime is fundamentally discrete or emergent is unknown. Whether singularities are resolved by quantum effects is unknown. Whether spacetime geometry arises from entanglement or other structures is unknown. These questions are active areas of research. Unknowable questions are different. They concern distinctions that no possible experiment could resolve, even in principle. If two theories make identical predictions at all accessible scales, then no observation can choose between them. In that case, the difference may not correspond to physical reality. Physics has encountered this before. Different formulations of quantum mechanics describe the same observable phenomena. The choice between them often reflects preference rather than experiment. Recognizing this does not weaken physics. It clarifies its scope. Some aspects of quantum spacetime may fall into this category. Certain details of microscopic structure may never produce observable consequences. If so, physics may describe limits rather than mechanisms. This does not imply that inquiry should stop. It implies that expectations should be realistic. The research culture surrounding quantum gravity reflects this awareness. Physicists working in the field are careful about claims. Progress is measured in consistency, mathematical coherence, and connection to known physics, not in dramatic predictions. Work continues across many directions. Researchers explore loop-based approaches, string-based frameworks, holographic models, and numerical simulations of quantum geometry. They refine mathematical tools, test internal consistency, and search for indirect observational signatures. This effort is distributed across universities, institutes, and collaborations worldwide. It is incremental rather than revolutionary. Advances are often technical and slow. This pace is not a sign of stagnation. It reflects the depth of the problem. There's also a recognition that new ideas may require new ways of thinking. Many foundational shifts in physics came not from extending existing theories, but from re-examining assumptions. The concept of emergent spacetime is one example of this. It challenges the assumption that space and time must be fundamental. At the same time, restraint is essential. History shows that radical ideas must earn their place through consistency and evidence. Elegant mathematics alone is not enough. Neither is philosophical appeal. The boundary of current physics is therefore not a wall. It is a transition zone. On one side lie theories that have been tested and confirmed repeatedly. On the other lie frameworks that aim to extend those theories into regimes not yet accessible. The boundary is defined by scale, by measurement, and by operational meaning. This boundary also serves a practical role. It prevents overreach. It reminds physics where confidence ends and conjecture begins. It keeps speculation anchored to what is known. At the same time, it provides direction. By identifying precisely where current descriptions fail, it highlights where new insight is needed. Singularities, Planck scale limits, and the incompatibility of quantum mechanics with dynamic spacetime are not vague mysteries. They are specific failures of existing frameworks. That specificity matters. It allows progress to be judged objectively. A new theory must reproduce classical spacetime at large scales. It must respect quantum principles where they are known to apply. It must resolve rather than hide the known breakdowns. Until such a theory is confirmed, the boundary remains. This does not diminish what physics has achieved. On the contrary, it reflects how far understanding has already been pushed. Few sciences can define their limits so precisely. The boundary of current physics marks not ignorance, but honesty. It distinguishes what can be said with confidence from what remains open. It separates established knowledge from active investigation. Recognizing that boundary prepares the ground for synthesis, it allows the central question to be revisited with clarity rather than expectation. What is known, what is unknown, and what may never be resolved can now be placed in proper context. From that position, the discussion can move toward integration rather than expansion. The aim is no longer to add more theories, but to understand how existing insights fit together, where they overlap, and where they must eventually give way. That shift signals the approach of a different kind of conclusion. Not one that resolves the problem, but one that places it within a coherent picture of what physics can and cannot say. After tracing the ideas, limits, and proposals that surround quantum spacetime, the original question can now be faced directly. Does spacetime truly become quantum, or is that way of phrasing the problem misleading? The honest answer is conditional. It depends on what is meant by spacetime, what is meant by quantum, and at what scale the question is being argued. At large scales, spacetime behaves classically. Distances are well defined. Time orders events reliably. Geometry responds smoothly to mass and energy. General relativity describes this behavior with exceptional accuracy, and no experiment has contradicted it. In this regime, spacetime does not appear quantum in any operational sense. At small scales, matter and energy behave quantum mechanically. Probabilities replace certainties. Measurements disturb what is measured. Discreteness and uncertainty are unavoidable. Quantum mechanics governs this domain, and its predictions are confirmed repeatedly. In this regime, spacetime is usually treated as a background rather than an object of study. The tension arises in the overlap between these regimes. When both gravity and quantum effects are strong, neither classical spacetime nor standard quantum mechanics can be applied without qualification. This is where the question of quantum spacetime becomes unavoidable. Different theoretical approaches answer the question in different ways. In loop quantum gravity, spacetime is quantum at all scales. Geometry itself is quantized. Areas and volumes take discrete values. Smooth spacetime is an emergent approximation that appears only when many quantum geometric elements are averaged together. In this view, spacetime does not become quantum at a particular point. It is quantum by nature, and classical behavior is a large-scale illusion. In string theory, spacetime remains smooth, but the objects within it are fundamentally quantum and extended. Singularities are avoided not because geometry is discrete, but because interactions are softened at short distances. Spacetime does not fragment. Instead, its role becomes secondary to deeper structures. In this view, spacetime may not need to become quantum at all. It may remain classical while being derived from quantum ingredients. In emergent spacetime approaches, spacetime is not fundamental in either sense. It arises from more basic quantum degrees of freedom that do not resemble space or time. Geometry appears only when those degrees of freedom organize in certain ways. In this view, spacetime never becomes quantum, because it was never fundamental to begin with. The quantum behavior lies beneath it. These answers are not merely different opinions, they reflect different assumptions about what spacetime is. If spacetime is treated as a physical field, like electromagnetism, then it makes sense to ask how it behaves under quantization. If spacetime is treated as an emergent description, then quantizing it directly may be the wrong approach. If spacetime is treated as a smooth arena softened by extended interactions, then discreteness may never appear. Each perspective is internally consistent. None is experimentally confirmed. What unites them is a shared conclusion. The smooth spacetime of experience is not fundamental across all scales. Whether through quantization, emergence, or modification, the classical picture fails when pushed far enough. Scale is the key variable. At human, planetary, and even galactic scales, spacetime behaves classically. At atomic scales, spacetime provides a stable background while quantum behavior dominates matter. At Planck scale conditions, the separation between spacetime and quantum behavior breaks down. This does not imply a sharp boundary in space or time. There is no location in the universe where spacetime suddenly changes character. There is no moment at which geometry flips from classical to quantum. The transition is scale-dependent, not spatially localized. The same region of space can be well described by classical geometry at one resolution and poorly described at another. Just as temperature ceases to be meaningful when only a few particles are involved, space-time geometry may cease to be meaningful when only a few underlying degrees of freedom are involved. This reframes the central question. Instead of asking when space-time becomes quantum, a more precise question emerges. At what scale do the concepts of distance, duration, and geometry stop being reliable descriptions of physical reality? That question has a clearer answer. Current theory strongly suggests that below the Planck scale, classical space-time concepts lose operational meaning. Distances cannot be defined without disrupting geometry. Time intervals cannot be resolved without invoking energies that destroy the notion of duration. Causality becomes difficult to define using familiar structures. Above that scale, space-time behaves smoothly and predictably. This does not require space-time to be literally quantized in the way energy levels are. It requires only that classical space-time is an effective description, valid within a certain range. From this perspective, asking whether space-time truly becomes quantum may be like asking whether temperature becomes quantum at small scales. The answer depends on context. Temperature remains a useful concept at large scales and fails at small ones. Its failure does not mean it was never real. It means it was never fundamental. Spacetime may occupy a similar position. This view also clarifies why progress has been slow. The question being asked lies at the boundary of what can be defined operationally. It concerns entities that may not admit direct measurement or clear distinction. It requires new conceptual frameworks, not just new calculations. That does not make the question meaningless. It makes it subtle. Physics advances by refining questions as much as by answering them. The journey from smooth space-time to quantum descriptions has already revealed where existing concepts hold and where they fail. That alone is a significant achievement. So does space-time truly become quantum? If the question means whether space-time must be treated using quantum principles at sufficiently small scales, the answer is likely yes. Classical geometry cannot be extended indefinitely. If the question means whether space-time is made of discrete quantum units, the answer is unknown and theory-dependent. If the question means whether space-time itself is a quantum object in the same sense as particles, the answer may be no. The most robust conclusion is this. Space-time, as currently understood, is not the final layer of physical description. Its smoothness, continuity, and stability are properties that apply within a certain range of scale. Outside that range, different concepts are required. This does not diminish the reality of space-time, it places it in context. Space-time works where it is used. It fails where it should not be used. That is not a flaw. It is how effective descriptions behave. The question of quantum space-time therefore resolves into something quieter but more precise. Not when space-time becomes quantum, but when space-time stops being the right language. That recognition integrates everything that has come before. It preserves the successes of general relativity. It respects the necessity of quantum mechanics. It acknowledges the limits of experiment. It avoids forcing incompatible ideas together. From this position, the discussion naturally shifts away from debate and toward reflection. Not reflection in the sense of speculation, but in the sense of understanding what physics can reasonably claim. Space-time may or may not be quantum in a fundamental sense. What is clear is that its familiar form is scale-bound. Knowing that is not the end of the story. It is the condition for asking the next question properly. Living in a universe with limits is not a failure of understanding. It is the condition under which understanding becomes possible. At human scales, the universe behaves in ways that are stable, predictable, and deeply familiar. Distances can be measured, time can be tracked, objects occupy places, events follow one another in reliable order. Smooth space-time is not an approximation in daily life. It is the structure through which reality is experienced. That matters. The fact that space-time may not be fundamental does not make it provisional or disposable. Temperature is not fundamental, yet it governs weather, biology, and chemistry. Pressure is not fundamental, yet it shapes stars and atmospheres. Smooth spacetime plays the same role. It is the correct description at the scale where human life, planetary motion, and cosmic evolution unfold. Physics does not aim to replace effective descriptions with deeper ones indiscriminately. It aims to use the right description at the right scale. Recognizing limits sharpens that aim. The search for quantum spacetime reveals that even our most successful concepts have domains of validity. Spacetime geometry works remarkably well across an enormous range of scales. It fails only when pushed into regimes where measurement itself becomes problematic. That failure is not an embarrassment, it is a guide. It tells us where not to extend familiar ideas. This perspective carries an important lesson about scientific humility. Physics progresses not by assuming that every concept must apply universally, but by identifying where concepts stop working. Knowing the boundary of a theory is as important as knowing its predictions. Smooth spacetime still matters because it is the language through which gravity, motion, and causality are understood in the world that can be observed. No proposed theory of quantum gravity replaces that fact. Any deeper theory must recover smooth spacetime as an emergent description, or it fails immediately. This places limits in their proper role. Limits are not barriers to meaning, they define it. There is a tendency, especially when discussing fundamental physics, to treat deeper explanations as more real than effective ones. This hierarchy can be misleading. Reality is not organized by depth alone, it is organized by relevance. The smoothness of spacetime is relevant to building bridges, navigating spacecraft, predicting eclipses, and understanding cosmic expansion. Its possible breakdown at unreachable scales does not weaken its authority where it applies. At the same time, the existence of limits prevents overconfidence. The idea that spacetime might cease to be meaningful at extremely small scales forces restraint. It discourages the assumption that intuition built from everyday experience can be applied universally. It reminds us that concepts such as distance and duration are tools, not absolutes. This restraint is not pessimism, it is precision. Scientific humility does not mean retreating into vagueness. It means stating clearly what is known, what is unknown, and what may never be expressible in familiar terms. The distinction between unknown and unknowable matters here. Some questions remain open because better theories or experiments may answer them. Others may be unanswerable because they ask for distinctions that have no operational meaning. Accepting this does not diminish inquiry, it refines it. Living in a universe with limits also shapes how uncertainty is held. Uncertainty in physics is often misunderstood as ignorance or failure. In reality, it is frequently the product of clarity. When physics reaches a point where questions can be posed but not resolved within existing frameworks, uncertainty is the honest response. This kind of uncertainty is calm. It does not demand resolution at all costs. It does not invent structure where none is supported. It recognizes that understanding is layered, and that some layers may not admit the same kinds of explanation as others. This calm uncertainty is visible throughout the study of quantum spacetime. Theories are proposed carefully, claims are constrained. Speculation is bounded by consistency with what is already known. Progress is measured in coherence rather than spectacle. That attitude reflects a mature science. It also has philosophical consequences. If spacetime is emergent, then the universe is not obliged to align with human intuitions about continuity and locality. If spacetime has limits, then reality is under no obligation to be fully describable in the language evolved for survival at moderate scales. This is not unsettling once it is understood properly. It is liberating. It means that physics is not failing when it encounters conceptual limits. It is succeeding in identifying them. It means that not every question needs an answer in order for understanding to deepen. Smooth spacetime remains the environment in which life unfolds. It is the arena in which meaning, causality, and experience take shape. That does not change if spacetime emerges from something deeper. Emergence does not erase reality. It explains it. The universe does not become less real when its foundations are questioned. It becomes more precisely understood. Living with limits, therefore, does not require resignation. It requires adjustment. It requires accepting that some aspects of reality are scale-dependent, and that descriptions valid at one scale may fail at another without contradiction. This acceptance has always accompanied major advances in physics. Absolute space gave way to relativity. Determinism gave way to probability. Each shift involved letting go of assumptions that once seemed unavoidable. The possible non-fundamental nature of spacetime belongs to that lineage. It is not an anomaly, it is a continuation. What remains constant is the role of careful reasoning, empirical grounding, and conceptual restraint. These principles do not dissolve at the limits of knowledge, they become more important. In the end, living in a universe with limits is not a philosophical compromise. It is a scientific achievement. It reflects the ability to map where understanding holds and where it must pause. That pause is not emptiness, it is space for reflection. Understanding that spacetime works where it works, fails where it should fail, and may not apply everywhere is not a loss. It is clarity without illusion.